Hi there. In this lecture, we're going to discuss this concept known as distributed shared memory. So far in the course, whenever we've assumed that processes communicate with each other over a distributed system, we've assumed that they use a network. This is a message passing network where a process sends a message and another process receives a message. But what if we allowed processes instead to share memory pages with each other, where processes might be able to write and read pages. So if a process wrote to a page number 5 and another process read from a page number 5, this would make it much more easier to write programs. We could then take programs that we've written for regular multiprocessor operating systems and then just run them over a distributed system where you have a network underneath. So you might be able to reuse programs as well. So this is the concept that is known as distributed shared memory, where you have processes sharing pages with each other, but in fact they're doing this over a message passing network that is underneath. So processes virtually share pages with each other, but underneath the underlying distributed shared memory system is implementing this by using message passing. Okay, so that's the main challenge over here. So distributed shared memory, in fact, is trying to achieve in software what has already been achieved in hardware in multiprocessor operating systems. So in multiprocessor operating systems, you have multiple processors sharing a common bus, sharing a common memory, and they already communicate with each other and they share the memory, right? So they share the pages of the memory. Now you want to implement the same thing in software over a distributed system. So it's the software version of multiprocessor communication, but over the network. Okay, so that's a main challenge over here. In fact, distributed shared memory and message passing are equivalent to each other in the sense that given a distributed shared memory system, you can implement a message passing system. You do this by sharing a common page as a buffer where you read and write messages. Essentially, you use it as a producer-consumer buffer. You can also do the reverse, where you can implement distributed shared memory over a message passing network, and we'll see how to do that in this lecture. So in order to do that, you need to maintain at each process a cache. A cache stores some pages that were recently accessed by that process. When the process wants to read or write a memory address in a page, it first checks if that page is present in the cache. If it is present, then it uses that version of the cache. If it's not, then it may need to fetch that page from somewhere else in the system. Yeah, so essentially, a cache is a collection of pages that have been recently accessed by the process that owns that particular cache. So you'll notice in this figure that every process has its own local cache. Typically, this cache is, of course, located on the same machine and on the same memory and on the same operating system as that process itself. Now, pages are typically mapped to the local memory of that process. The cache is mapped to the local memory as well. When a page is present in memory, it is called a page hit. So when the process tries to access a page and it is already present in memory, it's a page hit. However, if the page is not present in memory, it's called a page miss, and this leads to a page fault. Okay, a page fault happens in regular paging systems that are implemented by operating systems as well. And typically in a regular paging system in an operating system, when a page fault occurs, the operating system goes and fetches that particular block from the disk and stores it in main memory. In a distributed shared memory system, however, the page fault handler, the kernel trap handler that is invoked on a page fault, runs the distributed shared memory software, which then might fetch the page from a different process elsewhere on the network. Okay, and typically it does this by using multicast. So we're replacing some portion of the kernel in there with our DSM software. So essentially, distributed shared memory can be implemented in any system that involves paging by replacing the page fault handler and a few other pieces of software in there with appropriate software. So a few terms before we describe several scenarios. The owner is that special process that has the latest version of a particular page. So every page has an owner process at any given point of time. That process owns the latest version of the page. The owner of a page might change from time to time, as you will see as we go along. Second, each page is either in the read state or the write state. We note this as the R state or the W state respectively. When a page is in the R state, the owner has a read copy, but other processes might also have read copies. Okay, so this means that multiple processes are allowed to read a given page simultaneously. However, no write copies exist of that page. When any write copy exists, when a given page is in the W state, only owner has a copy of the page. No other copy of the page exists at any of the other processes in the group. This means that essentially writes are exclusive, but reads can be shared with other processes. Of course, here when I'm saying an owner has a copy, I mean that the owner has a copy of the page in its own cache. When I say a process has a copy, I essentially am meaning that the process has a copy of that page in its own cache. So let's discuss a few scenarios that might occur when a process is trying to do a read. Here, in all of these scenarios, process 1 is attempting a read, and there are 6 scenarios I'm going to discuss here. In this first scenario, the process 1 is the owner of the page and has the page already in the R state. In this case, the read is served directly from the cache of process 1, and no messages need to be sent out over the network. So that's the first scenario. Let's look at the second scenario. In the second scenario, the process 1 is the owner of the page and the page is in the write or W state. Once again, in this case, a read by process 1 can be done directly from the cache, and it does not need any messages to be sent over the network. In the third scenario, the process 1 is the owner, has the page in the read state, but there are a bunch of other processes that also have the same page in the read state. In this case, processes 3 and 4 are in the read state for that given page. Once again, process 1, when it reads the page, the read can be served from the cache and no messages need to be sent. The fourth scenario is where, similar to the third scenario, except that someone else is the owner, and once again here, the read can be served from the cache at process 1 and no messages need to be sent. Now let's get to the other scenarios which need something else to happen. So in the fifth scenario here, process 1 does not have the page in its own cache. Other processes have the page in the R state. So in this case, processes 3 and 4 have the page in the R state. In this case, process 1 asks for a copy of the page. For this, it uses multicast inside the group of DSM processes here. When it sends out a multicast message asking for this particular page, say page number 5, then the owner responds back with the latest version of the page, and then process 1 marks the page as R, as in read state, and then it can do the read directly from the cache itself. So the end state in this particular case would look like this, where process 1 would fetch the page and then mark it as R and then do the read from itself. Let's get to the sixth and the final scenario, where process 1 is trying to read the page and there is a write copy of the page located elsewhere, in this case process 4, which is also of course the owner of that page. In this case, process 1 needs to ask the other process to degrade its copy to the read mode. It locates this process via multicast, so essentially it sends out a multicast to the group. The other process, that is the owner, responds back to the multicast saying, hey, I am the owner. So process 1 fetches the page, marks it as R, and it does a read. And in the meantime, process 4 also degrades its copy from a W to an R. So the end state in this case looks like this, where process 4 has changed its copy from W to an R. It still retains a copy of the page so that it can continue to read it. And process 1 also has a read copy of the page so it can continue to read it. Process 4, if it wanted to write the page again, it would then need to do something else. It cannot write this page as is in this particular state. So let's discuss what happens with writes. So here is one scenario for a write. Process 1 is trying to write a given page, and it is the owner of the page, and it has a write copy of the page. In this case, the write can be done directly to the cache and no messages need to be sent out over the network. Second scenario, process 1 is the owner of the page. It has the page in the read state, and other processes have the page in the read state. In this case, process 1 needs to ask the other processes to invalidate their copies of the page. Okay, so it does this by using multicast. It sends out a multicast message saying, hey, please invalidate all your copies of the page. I want to do a write. Once this is done, it marks its own copy as W, meaning it can be now written, and then it does a write in this particular state. So in this case, you'll notice that processes 3 and 4 have invalidated their copies of the page, so they can no longer use that copy of the page. If they want to do any operations on that particular page, they'll need to fetch a new copy from the new owner. In the meantime, process 1 now has a write copy of the page, and it can go ahead and do both reads as well as writes on this copy. So that's the second scenario for the write. Let's discuss the third scenario. In this case, someone else is the owner, and process 1 has the page in the read state. Once again, this is similar to the previous case, except that the process 1 now additionally needs to become the owner. So the other processes are asked to invalidate their copies of the page. They do so. Processes 3 and 4 do so here in this particular figure. And process 1 gets the ownership of the page as well as marks the page as W and then does a write on that page. And here's a fourth scenario. Process 1 does not have the page at all. Other processes have the page in either the read state or the R state or the W state. In this case, I've just shown the R state, but it doesn't really matter. The operations are similar if other processes have it in the write state as well. Essentially, process 1 asks other processes to invalidate their copies of the page. Again, it uses multicast for this. It fetches all copies, it uses the latest copy, or it can just fetch the copy directly from the owner. It marks its copy as W and it becomes the owner. Other processes 3 and 4 in this case invalidate their copies of the page, so they can't use that copy anymore. They need to fetch a copy from the latest owner. So even though the slide here says fetch all copies, you really don't need to fetch all copies. You just need to send out a multicast and have only the owner respond back to you with the latest version of the page. So that is known as the invalidate approach, where when you do a write and other processes have a copy of the page, you ask them to invalidate their copies of the page. The invalidate approach works well in many of the cases. However, there are some cases where you might have bad behavior in the invalidate approach. If two processes write the same page concurrently, for instance, if they're writing different variables that happen to reside on the same page, then this may result in flip-flopping behavior where one process invalidates the other, and then soon after the second process invalidates the first one. And this involves lots of network transfer, because essentially on every invalidate you fetch the new copy of the page over to another process. Okay, so this is what is known as false sharing, when unrelated variables fall on the same page, and this results in flip-flopping behavior in the invalidate approach to distributed shared memory. Essentially what's happening here is that false sharing happens when the page size is so large that it captures more than the locality of interest. So every process has a locality of interest, which is typically the window within which it is accessing variables and changing variables. The page size needs to be just about the locality of interest. But this is of course hard to know, because the locality of interest depends on the application, it depends on the processes themselves, and of course it can vary over time. In general, you want your page size to capture the locality of interest. If the page size is much larger, you can have false sharing, where different processes have variables on the same page and results in this flip-flopping behavior that we just discussed. If the page size is too small, then you're capturing only a small portion of the locality of interest, and you end up incurring too many page transfers. There are way too many pages in the system, and so you incur a very high overhead in transferring these pages, and this also is very inefficient. So setting the page size is an important concern in distributed shared memory systems. You want it set not too high, but not too low either. An alternative approach to the invalidate approach is what is known as the update approach. In this approach, multiple processes are allowed to have the page in the write state. So unlike in the invalidate approach, where at most one process could have a given page in the write state, here multiple processes are allowed to have a given page in the write state. When a process writes to a page, it does not invalidate the other processes. Instead, it sends them multicast saying, hey, I have written the bytes at address so and so with these new values. Please update your copies of the page. Okay, so that's why this is known as the update approach. On a write, you send update messages to the other processes that are currently holding write copies of this page. So in this way, the other processes can then continue reading and writing this particular page. The update approach here is preferable over invalidate under some situations only, when there is a lot of sharing among processes, when writes happen to very small variables, and when page sizes are very large. But in general, though, the invalidate approach is the more preferable approach, because it tends to work well in more of the cases, more of the realistic cases, than the update approach. Consistency. Whenever you have multiple processes sharing data, such as pages, consistency comes into the picture. We have discussed consistency before. We have discussed several consistency models when we discussed key value stores and NoSQL storage systems. And those same consistency models apply here as well. Those include linearizability and sequential consistency, very strong models. Causal consistency, FIFO consistency, which otherwise is known as pipeline RAM consistency, and also eventual consistency. There are also other models such as release consistency that originated from the distributed shared memory and the multiprocessor architecture areas, and these should be familiar to you from earlier in the course. In fact, all of these terms that you see here originated from the area of hardware architecture and multiprocessor architecture, as well as distributed shared memory, and then later on they were adapted by key value stores and NoSQL storage systems, because after all it's the same concept there where processes share certain memory. So as one goes down the order, as you know, the speed of the system increases, the speed of reads and writes increases, but of course the consistency gets weaker and weaker. So distributed shared memory has been a very popular area for a while. It was popular up until about a decade ago, and then it started falling in popularity. But some have surmised that it may be making a comeback now with faster networks like InfiniBand and other faster networks, as well as with solid-state drives and other newer versions of solid-state drives coming into the picture. Remote direct memory access, also known as RDMA, where one machine or a processor on one machine accesses the RAM of another machine over the network, that is becoming more and more widespread now. It's becoming more realistic now. And only time will tell whether DSM or distributed shared memory will make a comeback and become more widespread in today's machines. As of now, it's not really very widely used today. So we've discussed distributed shared memory where processes share pages instead of sending and receiving messages. This is a useful abstraction to write code where if you've written code for processes that share the same memory over one operating system, now you can simply take the same code and run it over a distributed shared memory system where these processes are instead at different machines communicating over a network. So distributed shared memory essentially provides a virtual abstraction of processes sharing pages, while underneath it is running over a message passing network. So distributed shared memory can be implemented over a message passing interface and also vice versa. So these two forms of communication are in fact equivalent. And we've discussed two different flavors of implementing distributed shared memory. They are known as invalidate, which is a more popular approach, and update, which is a less popular approach, but is an alternative available to you.